And the webinar will be recorded. Yeah. Okay. Good. All right. So thank you everyone for joining us today. So I'm Laurie Pallas. I'm Global Application Manager for the Electron Microscope Analysis at Bruker Analytics in Berlin. And I will be the host for this webinar. So our presenters are my colleague, Dr. Michel Abratis from Bruker, Berlin, and Dr. Eric Robin online from the Atomic Energy Commission based in Grenoble in France. In this webinar, we will review how the addition of a Grazing incidence X-ray optic to WDS can allow to conduct measurement at low probe current, enabling high spatial resolution application. So first, I will introduce our two speakers. Eric. Eric Robin is a senior researcher at the Alternative Energies and Atomic Energy Commission (CEA) in Grenoble, in France. He holds a PhD in nuclear physics and spectroscopy, and from Morsing University in Paris, he holds the national highest education diploma, habilitation in French, required to be responsible to conduct research. During his professional career, Eric has developed analytical tools for particle analysis at the CEA in Saclay. In 2012, he joined the LEMA group for Laboratory for Study of Materials by Advanced Microscopy at IRIG, the Interdisciplinary Research Institute of CEA in Grenoble. He's responsible for training, research, development, and application of EDX and WDX spectrometry in SEM and in TEM within the nanocharacterization platform called Minatech. Eric is co-author of more than 200 scientific publications in peer-reviewed journals and conferences proceedings, as well as 21 popularizing works and 7 educational books. He has directed many public conferences, as also invited speaker, and participated in many radio and television broadcasts. And my colleague, Michel Abratis, studied geology at the University of Kiel and Göttingen, where he also received his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michel set up and managed a microprobe lab at Jena University before joining the Bruker Analytics group as senior application scientist in 2015. And so just before we start with the presentation, I'll give you just some very short housekeeping details. So you see the outline slide of your screen. The webinar is recorded, it's interactive, so you can ask your questions at any time in the question and answer Q&A window that should be on the right side corner of your screen. The presentation will last about 40 minutes, and then we'll end by a live Q&A session with your questions. If we run out of time and are able to get to your questions during this event, we will follow up with you by email. And the webinar recording will be available very soon, as well as the slides. So this presentation is divided in 4 parts. I guess you see my, not really, a mouse. No, okay. So first, Michel will review the WDS technique and the advantages of using parallel beam optic approach with grazing incidence, and how WDS can complete the EDS analysis, especially, for instance, when analyzing light trace element or to solve peak overlap. Then Eric will present some of the latest application examples from the CEA on the characterization of boron-rich phases in permanent rare earth magnets, so permanent magnets using used, for instance, in the engines of electrical vehicles, and also an example on quantification of the magnesium dopant in gallium nitride nanowires. And then we'll have the conclusions and Q&A. So now I will leave it to Michel.
Yeah, thank you very much, Laurie, for the introduction, and hello everyone in the audience. Before we get to some very exciting applications shown by Eric, I will start with a brief introduction of the technique of the WDS. So what is a wavelength dispersive spectrometer? And we will see that here. And the next slide. Go on. So, okay, so in an SEM, when we investigate a sample, we are using electrons, primary electrons from the SEM gun, and they induce the backscattered electrons and secondary electrons expelled from the sample, and this is used for imaging. But there are much more effects generated in the specimen. So, for example, the X-rays are generated by exciting the atoms of the sample. And this is what we can use for analysis of the chemistry of the samples. And we commonly use the EDS detector, the energy dispersive spectrometer, because it's convenient. And yeah, so there's a second technique, that is the WDS, the wavelength dispersive spectrometer. And this also has some advantages. Both detectors determine the same parameters, the X-rays, so the characteristic and the background X-rays, but with different technique. And what are the differences? I will explain here. So all WDS, they are using crystals for diffraction of the X-rays. And this diffraction relies on the Bragg equation. So what is the fundamental of this technique is, where's my mouse here somewhere? We are focusing one energy or wavelength of the X-rays towards our detector, and the parameters inducing that are the crystal lattice parameter D, and the incidence angle of the X-rays, the angle theta. So this graph here, this scheme shows how the X-rays in green, the X-rays generated in the sample, they are reflected on the crystal lattice of an analyzer crystal, here symbolized by the red dots. And when with a certain angle theta, when these waves are then well in phase, this means constructive interference, and the resulting wave will be then a very intense wave, and all the other wavelengths will be filtered out. So this is the monochromizer effect of an analyzer crystal. And how it looks like in the WDS is shown here. The core part of any WDS is the diffractor system. Using crystals or multilayer elements, we are using up to, or we offer up to 6 crystals covering the entire energy range that can be analyzed. And these analyzer crystals, they act as monochromators. So from a polychromatic X-ray beam, they filter out, intensify one certain energy, one wavelength, and this wavelength of X-rays is then reflected towards the detector that is simply a counter, so just counting the intensities. And what energy is detected here depends on the theta angle, and with a changing angle, we reflect a different energy towards the detector. So, and to cover the entire range, we can also change the crystals so that we will finally be able to analyze the entire periodic system. Now let's have a look on some more advanced WDS systems using an optic, a parallel beam optic. So we start with a classical system. This is a so-called Rowland circle system, where sample, diffractor, and detector are sitting on a so-called Rowland circle with a constant diameter. The system is guaranteeing that the focus point is always in the detector. So whenever the angle of the diffractor changes to reflect a different X-ray energy towards the detector, the diffractor has to move along the circle also, and the detector as well. And only that will guarantee that the focus is right in the detector. A more advanced system is using a collimator optic. This collimator optic captures a maximum of X-rays close to the source of origin, close to the sample. And the diverging X-ray beam is then converted into a parallel beam that hits the diffractor and filters out one certain energy. The main difference between the two systems is the solid angle. The solid angle omega, which means the amount of X-rays that can be captured. And this depends on the surface of the detector or the diffractor in the case of a WDS, and the distance of the detecting system towards the source. The distance is d, and you can clearly see the d value is much lower here with a collimator optic, with a parallel beam system, than with the classical Rowland circle system. And that means the solid angle is much larger for a system, for a design with a parallel beams optic than with a classical system. So a classical system has a small solid angle. That means to have a sufficient signal, it requires a very high beam current or very long acquisition times. And both the long acquisition time or the high beam current, they both may cause damage to sensitive samples. The parallel beam optic design guarantees a high solid angle with the optic close to the sample. That means in reward, we can operate with very low probe currents, and the system is faster and causes less damage. There are different types of parallel beam optics available. Some two end members are the Grazing Incidence optic on the left side, on the right side, the polycapillary optic using optic fibers. Bruker is using the Grazing Incidence optic, where metallic, conic metallic mirrors reflect the diverging X-rays and convert them into a parallel beam. Advantage of such a system is the very high spectral resolution compared to other parallel beam optic systems. It has a lower transition for the high energy X-rays, but it's optimized for the low energy X-rays. And this is what is most crucial. So as we see here in the spectrum, so peak resolution is quite nice here in the higher energy range, also by EDS, but we have a severe crowd here. So it's very strong overlap at the low energy region, and the Bruker system can resolve this. So now let's have a look on the outcome. What is the advantage for you? So what can WDS add to your microanalysis with EDS? And to answer this question, we have to compare the parameters of WDS and EDS. One parameter is the spectral resolution, shown here in this graph in terms of the width of the peaks, the full width half mean, so how broad are the peaks, in respect of the energies analyzed. And we analyzed a lot of different elements, different lines, K lines, L lines, M lines, not shown here. And we compare the EDX with the black line. EDX shows peak widths between 40 and 110 electron volts in this range. And WDS shows much narrower peaks. So the half width is much lower. The half width depends on the energy of the X-rays, but also on the different analyzer crystals. And this is shown here. PET is one, TAP is one, and here multi-layer elements with different angstrom lattice spacing. So to cover the entire energy range, we need these different diffractors, and they show different properties. In conclusion, what we can see from this graph, resolution of the WDS is much higher, up to 20 times higher. For example, the silicon K alpha is 3.5 electron volts for the WDS system and 70 electron volts for the EDS system. So, so we can much better resolve overlaps. Another parameter is detection limit. So this determines how good we can determine trace elements. in the sample, and we compare here once again EDS with a black line, and the colored lines show WDS. These are measured parameters, so measured values, measured at fairly low primary energy, only 10 kV, 5 nanoampere. So these are the results from these low energies. And with higher energy, we would clearly get even better values. So the minimum amount for EDS is 0.1% as detection limits, and we are 10 times better with the WDS. So we can determine traces of 100 ppm even for light elements. So even for the very low X-ray energies, light element boron, we can detect traces of 100 ppm. So from this, we can conclude some applications which are very suitable for the WDS. This shows some examples, just the fields of application. And one field is wherever we need resolution, spectral resolution. It makes sense to apply the WDS. Here it's a microelectronic device separating the silicon K alpha in green here from tungsten M lines in red. And yeah, this can be done in spectra, but also in maps. In the center part, trace element detection. So here are some traces of the element strontium shown in a silicate mineral. So we see here the distribution of trace elements. And on the right side, this shows the performance for the low energies. This is mapping of the light element carbon in a two-phase steel, so with higher carbon phase martensite next to ferrite in the steel. To conclude this, here's an overview of the characteristic, the advantages and disadvantages of EDS and WDS. The EDS has a somewhat limited spectral resolution and lower peak to background ratios than WDS. On the other hand, it covers the entire energy range, and it's fast since we acquire the entire spectrum just at once. On the other hand, the WDS shows much higher spectral resolution, up to 20 times higher. It shows higher signal-to-noise ratios, so 10 times higher, which also means 10 times lower limits of detection, so very good for trace elements. And a third point, which is special for a system like ours with the Grazing Incidence Optic, is the outstanding sensitivity for the low energy X-rays, which means we can nicely determine light elements, but we can also nicely apply it to low kV applications. So which allows us to operate with very high spectral, with not only spectral resolution, but very high spatial resolution. And Eric will give some examples on such applications with high spatial resolution. The upper energy range is limited. The system is optimized for the low energy range, which makes some sense. And the measurement is slower since it's sequential, measuring one element after the other or one energy after the other. So combination of both is the solution, the best solution. The WDS is an ideal technique to complement the EDS for demanding applications. And some of these applications will now be shown by Eric. And with this, I hand over to Eric. Please go ahead.
Okay, thank you. So I'm going to present you to, hi everybody, first I'm Eric, and so I'm going to present you two application examples of the WDS XN spectrometer from Bruker for the advanced chemical analysis of nanostructure. So, well, as I said, I'm going to present you two application examples. And, well, starting with the first example, which is the identification, characterization of rare rich phases in recycled magnets. And well, these, of course, are these magnets are essential for the development of electric vehicles and wind turbines, and the demand for the European market is expected to increase by a factor of 5, and for the automotive market and 3 for the wind market over the next decade. However, rare earths, and particularly heavy rare earth elements such as dysprosium or terbium, are critical elements which constitute an economic and strategic issue for Europe. So the recycling of used magnets has become essential. It is a complex process, the recycling, that must be optimized in order to reduce the use of rare earths while maintaining good magnet performances. So for this, it is essential to be able to identify, characterize the rare earth rich phases which form during the recycling process. Here, it is an image of such a small region of the magnet taken by SCM, showing the recycled magnet, which contain different phases. In red, some dysprosium-rich phase, and while in green, some neodymium-rich phase. And well, in this kind of magnet, what we are interested in general, the two phases, which are what we call the 2-14-1 phases, which contain 2 atoms of rare earths with 14 atoms of iron and cobalt, and with 1 atom of boron. And there is another, so this is the main phases that we are looking at. And the second phase that could be formed is the 1-4-4 phases, which have this composition. And so the problem we have here, we have 2 problems in identifying correctly these phases and characterizing their composition. First, it is the overall dimension of these phases, which are about 600 nanometers for the most large phase, but with dimension which can be as small as 200 nanometers. And so here I have represented what I call the X-ray spatial resolution in ADX, which is not the beam resolution. The electron beam resolution is a few nanometers when you are performing some secondary electron images. But the X-ray resolution strongly depends on the energy of the beam. Because the electron beam interact, the volume of interaction of the electron beam is quite important in material, in massive material. And this interaction is defined by this relation, which gives you the diameter of the overall volume of ionization of the atoms of the material. And this diameter depends on the energy of the beam, but also on the edge energy of the shell you are ionizing for the considered element. For instance, for gallium, the edge energy is about 10 kiloelectron volt, and we consider that it is necessary to have about 1.5 or 2 times this energy to measure correctly this element. So for dysprosium, for instance, we need at least an energy, minimum energy is about 12 kilovolt or up to 15 kilovolt. So you see from this diagram that if we use 15 kilovolt, the minimum spatial resolution we can get is 600 nanometers. I mean that X-rays are coming from all this region, which is 600 nanometers. So it's not possible to measure small particles as small as 200 nanometers. So the first problem is a problem of X-ray spatial resolution, which is quite limited if you work at relatively high voltage, and if you want to measure the K line and R line of your element. And in general, it is in this region we measure this rare earth element, as well as iron and other elements, because of course, in general, in that region, the X-rays are relatively well separated, which is not always the case as shown here on this figure, because you see that you have strong overlap between dysprosium and iron, for instance, and which is so far difficult to measure low concentration of dysprosium inside this sample. And we have the same problem with cobalt, which also overlap with the K-beta line of iron. Well, so the first thing would be to reduce the energy of the beam, because if we work in the range of few kilovolts, then we can reach very relatively low. We can have relatively good spatial resolution as low as about 100 nanometers if we work at 5 kilovolt up to 400 nanometers. So at 5 kilovolt, for instance, we are able to measure very small inclusion at this one here. So the first thing is to test, of course, this part, and to do that, I propose to show you just a very simple protocol to do that. Here we have a sample which contains some ferrite, which is pure iron inclusions of different sizes, 400 nanometers for this one and 125 nanometers for this one, which are embedded in a material which contain a lot of dysprosium. So here in red, I have represented the spectrum, ED spectrum from this phase that show you the dysprosium peak and also neodymium peak and iron peak. So this spectrum was acquired at 5 kilovolt with 5 nanoampere. And so the objective here is just to use at 5 kilovolt to test if indeed we are inside this inclusion and inside this inclusion, which is the case for the inclusion of 400 nanometers, because we do not see the dysprosium peak. And for this small inclusion, we see here a very small contribution of the surrounding matrix in our spectrum. So it means that this relation works well, and that indeed we are able to work at relatively low voltage to measure the phase itself and do not have any contribution from the surrounding matrix. Well, so this is the same spectrum obtained at 5 kilovolt and 5 nanoampere. This is the ED spectrum. And the problem now we have the good resolution, but we still have a lot of overlap between different X-ray lines, like cobalt with iron, praseodymium, neodymium, and gallium, also dysprosium, which may interact with neodymium. And the last problem we have is that it is very difficult here to measure boron, because boron is a soft X-ray which is strongly absorbed in the window of the detectors and the dead layer also of the crystal. So it's particularly hard to extract low concentration of boron. As a result, we cannot clearly identify the phases, even if we have the resolution, because we do not measure boron, and the result for the rarest element do not correspond to an expected spectrometry in this material. And so the solution is to rely on the WDS, because with the WDS, we can separate all X-rays as shown here. Dysprosium, here we can see the M-alpha and beta, but we can separate all X-rays and we can choose which one we want to use to make the quantification. It's not necessary to measure all X-rays line, of course. We just have to measure the maximum of each X-rays. Here it is a scan of all the samples, so a scan is quite long to acquire, but for measuring very rapidly this line, you just have to measure the maximum here and the background on each side of the peak. And so relatively rapidly, you can get good signal from the different elements which are present. And you see that now we can separate cobalt from iron. We can see the M zeta line of neodymium. We can extract the praseodymium M beta line. But for instance, here we cannot extract the praseodymium M gamma line, which overlap with the gallium K alpha, gallium K beta line here in that case. But we can rely on this X-ray line. And as you see here for neodymium, we have also an overlap with the dysprosium M gamma line. Sorry, rapid. And then, but we can use for neodymium either the M zeta or M alpha or M gamma line. So we always have an X-ray line that we can analyze using this WDS, working at 5 kilovolt and a relatively small small beam current for this analysis. And the last point is that now we're particularly sensitive for the detection of boron. So here you can compare the result obtained with WDS with that one obtained for EDS. And so now we obtain the correct stoichiometry, which is indeed 214.1 phase, which are present here. And so we can do the same for the second phase, which is the small one, in fact, here. And we acquire also the spectrum. Here we can see that obviously there is much more boron in this material. And the question, of course, is to confirm that this phase is indeed the 144 phases, which is suggested by the result of EDS that we do not have exactly the same the stoichiometry we expect. And so when we rely with the WDS, here again, we obtain the correct stoichiometry for this phase. So with this detector, with this spectrometer, it's possible to do this kind of analysis by reducing both the voltage and work at relatively beam current. And the last example, of course, is, as I said at the beginning, it's necessary to identify all the phases. So this is an analysis of the neodymium-rich phases in green here. And in this phase, this show the, so it's a quite a large phase, so we can use voltage, a higher voltage of 10 kilovolt here. And in this phase, you see that, in fact, it's a complex spectrum. Of course, you can do the deconvolution in the ODS spectrum, but the composition you obtain is very quite difficult to say if it is correct because of the huge overlap of the cobalt with neodymium, with iron, praseodymium, and so on. And here you can see the good efficiency of the WDS because you can clearly separate iron, neodymium, cobalt, copper, and praseodymium, terbium, and all X-ray line. And so you can also measure here that you have a small amount of boron. And so to extract a composition which reflects the composition of this phase. Well, so this was the first example. And the second example I would like to talk about is quantification of magnesium dopant in gallium nitride nanowires. So rapidly characterizing doping is essential for the understanding and improvement of electrical and optical properties of semiconductors in order to produce reliable and performant electronic and optical devices. So the increasingly reduced dimension of semiconducting devices, as well as the development of new nanomaterial-based devices such as nanowires, require the characterization and quantification of relatively low level of dopant at the nanoscale. And so this represents a real challenge that is not fully achieved today by existing techniques. There are some techniques which are able to measure, of course, low concentration of dopants. But the problem here again is to combine the possibility to measure low concentration on a very, very small, at a very, very small scale. So here it's an example of what we can do on a single nanowire. So the nanowire here is composed essentially of the first layer of gallium nitride, which is doped with magnesium, and it is the concentration of this element, magnesium, that we want to measure. We do not know exactly the thickness of this cap, and so it is expected that it is larger than 50 nanometers, so we have to confirm this. Thereafter, we have a small layer, which is less than 50 nanometers of aluminum gallium nitride. And then after, we have a substrate of indium gallium nitride. So what we can do here, again, is to look at this relation between the X-ray resolution and the energy of the beam. And the first thing we do is to work first at 10 kilovolts to get the first spectrum, a DX spectrum that I show here. But 10 kilovolts, you see that we should penetrate about 500 nanometers. But on the spectrum here, what we see is that we can see, of course, the L line of gallium, the K line of aluminum, which is present, which tend to indicate that probably we reach this layer here. But here we can see the nitrogen K line and possibly the M line of indium. Well, for indium, it should be possible at 10 kilovolt to look at the L line of indium. And in fact, the main problem is that here with the EDs, we cannot clearly identify magnesium because magnesium strongly overlap with the gallium peak, especially because the concentration is quite low. So it's not possible to extract the magnesium concentration here. But if you rely on the WDS, this is the same spectrum with the WDS we acquire. In that case, what we see is that at this voltage, we have first small peak, which is the M zeta line of indium, which appear here. And this is the K line of nitrogen, which was masked by due to the poor resolution we had by EDS. But with the WDS, we are able to resolve these two peaks. And again, what we can see here is that we have a small peak of magnesium which appear, which was not seen, of course, here because of the poor resolution and also because of the small contribution of this L beta 3-4 line. And so here it means since we have indium, we have magnesium and aluminum, that probably we penetrate down to the substrate. So we reduce the voltage at 4 kilovolt to penetrate only by 100 nanometers in the substrate. And now you can see that on this second spectrum that first the indium contribution disappear from the spectrum. It means that we didn't reach the substrate, and the aluminum also disappear from the spectrum, so we did not reach this layer. So we are only inside this layer, and it means that the layer is probably at least 100 nanometers thick. So it would be possible to continue to vary the voltage by increasing now the voltage slowly to see when aluminum peak appears, when at the indium peak appears, and so we are able to determine the exact, well, approximately exact thickness of this layer and thickness of this layer. And it's also possible now to measure the magnesium concentration from this peak here, and which is about 0.08 weight percent. So we are able to measure some dopants, and we did that for the dopants like silicon, phosphorus, and different dopants in different lines. Okay, so, well, my motivation for WDS and SCM, of course, is that, as I have shown, WDS, this X-sense detector perfectly complement our ADS detector with higher spectral resolution, resolving peak overlaps, and we have the resolution instead of deconvolution, which induce sometimes many error in the quantification process, especially when you have overlap, when X-ray lines overlap. And well, the possibility to analyze precisely light and trace elements with relatively low, very good detection limit, including beryllium and boron, and with few hundred ppm, and sometimes it's possible below. And of course, it offered the capacity, the ability to work at low voltage, and so to get very high spatial resolution. And sometimes we can, depending on what we want what the element we are looking at, especially if we look at very soft X-rays, it's possible to get very high spatial resolution, few tens nanometers. So it depends the way of the analysis and then the structuring SCM. So thank you for your attention. If you have any question, I would be pleased to answer them.
Merci, Eric. Thank you very much for this great presentation and for sharing your results with us. And we will now move to the Q&A session. So, which slide it is? Be able to type in. Okay. All right. So we are now in the question and answer session. So you can submit your questions using the little box window on the right of your screen, right side of your screen. You can see the little question mark, and just write it down and press send. And in the meantime, we have received a couple of questions. So I will start with the first one. And I think it's for Michel. Yes. Is WDS sensitive to any change in working distance or setup? Okay, so yes. Deborah? It's okay otherwise.
Yeah, can you hear me like this?
It's the one from your laptop.
Okay, so sorry. What was the question about working distance? And
yes, how changing working distance or setup, how WDS is sensitive to such changes?
Okay, so any WDS is sensitive to the working distance. It operates at a fixed analytical working distance, and so because of the Bragg equation. So this requires that the working distance is fixed. And with our system, it's easy to confirm that, or we set it up to the analytical working distance of the respective system. And then we do the final focusing with an automatic system. So we acquire the image of the sample. We select an X-ray line, and then we let the system look for the maximum signal while adjusting the position of the optic in vertical and horizontal direction. So it's automatic, and that helps a lot to set it up correctly.
Thank you, Michel. Question for Eric now. Is it possible to analyze nanostructures of a few tenths of nanometers?
Yes, it is. It's possible to do that, but it strongly depends, in fact, on the element you are looking at, because you need, well, I have an example of this kind of that. Maybe I can share it. Wait. Yes, maybe this one.
Let's try, otherwise I'll try on my side. So it's not sharing. Are you sharing now?
Yes, now.
Yes, it works.
Yes,
The
it
way
works.
it's intended. Awesome.
Okay, well, so wait a minute. Up. Yes, okay, so you see the slide?
Yes.
In fact, this is just the problem of measuring niobium in zirconium materials. So the problem was to measure the concentration of course, by ADX, you have a strong convolution between zirconium and niobium. Of course, it's possible to perform some deconvolution. Here we see that it's possible to work at high voltage, but as I explained, you still have the problem that high voltage, the spatial resolution is very, very bad. If you use 5 kilovolt, the spatial resolution is better. You can get spatial resolution of 100 nanometers, still measuring the X-ray line by WDS of niobium and zirconium, which are clearly well separated. But you can also use the M-zeta line, and the M-zeta line are at very low energy. So you can work, and it's what we did, at 1.5 kilovolts. And at this voltage, you can get very good results because you can separate clearly zirconium and niobium. Well, of course, it's necessary to use zirconium and niobium standard absolutely in the same condition and to prepare very carefully the sample, because for such soft X-ray line, absorption in any type of contamination at the surface of the material problematic. So as you see, in that case, you can measure at 1.5 kilovolt layer as thin as 20 nanometers, and it's possible for this X-ray line to work. We didn't test, but to work theoretically at 0.5 kilovolt. In that case, you should get 2 nanometers, which is about the spatial resolution of the electron beam. So, well, it's possible to have very good spatial resolution, but it depends on the element you are looking at.
Thank you, Eric. This actually answers a couple of questions. I had a similar one for Michel, how sample preparation, how important it is to WDS measurement, and what are the requirements, I don't know, in terms of polishing, for instance, or if you want to add something to...
For sample preparation, so yeah, it's important for every kind of standard-based analysis. So also EDS, standard-based analysis, you have to make sure that your sample is well prepared so that you have a very smooth, well-polished surface, and that the sample is not charging. So you need to coat the sample if it's not conductive in itself. And yeah, polishing is important. Otherwise, you will lose some X-rays, and standard-based quantification always means you're comparing, and you have the ideal well-polished standard, so you also need a well-polished sample.
Thank you, Michel. And actually, this is linked to that question for Eric. Is it possible to quantify the WDS spectrum without standards?
No, not yet. Theoretically, it should be, but in practice, it is not. There's always a big difference between theory and practice. But in practice, no, it's you need standards for different reasons. One reason is that you need standard, and on these soft X-rays, particularly the L and some M X-rays, you can have different results if you use standard which are not of the same structure or very different in their composition from the material you are analyzing. This is a constraint for the use of WDS, because in general people want to be fast in their analysis, and in general I have the remark that we're using standard, it's a problem and so on. But if you have standard, in fact, you can measure, you measure the standard ounce time only, and then after it should work during many years if you don't change your detectors or you do not modify your geometry. It is not a problem. So you have to spend sometimes at the beginning to use standard to calibrate your system, and then after it will work.
Thank you. Next question for Michel. Does Esprit have a capability to do WDS quantitative line scan?
Yes, sure. We can do that. So both line scans and also mapping can be done quantitatively. So not just qualitatively, which all, yeah, in most cases with WDS, it's already sufficient because we have this high resolution, but we can do it also quantitatively. But remember, for a quantitative measurement of a line scan or map, you need to acquire also standards. So you need both your sample and standards. And for the line scan and mapping, you have to measure on the peak, but also on background positions to subtract the background noise and calculate net counts. So it will take a little bit longer, but it's possible, sure.
Thank you. Maybe another question for Michel. Why is your system more efficient on low energies?
Yeah, like I showed, the system has a very high solid angle, and that is due to the optic, the parallel beam optic, and especially this grazing incidence optic with the metal cones, so it captures a maximum of X-rays, and so that's one point, the optic itself and the optic close to the sample. And the other effect is also given by the diffractor crystal or the multi-layer analyzer. So the for soft X-rays, we need multi-layers made of several layers of metals instead of crystals. Crystals just cover the energy range up to about 500 electron volts. So for the lower energies, we're using multi-layer elements, and the ones that we are using are very efficient for the low X-ray energies.
Thank you, Michel. We have time for one last question. I'll let Eric or you pick up one of your choice.
Well,
if it's too long, we can do it very afterwards. No worries.
No. There was a question about the timing to get enough count for resolving light elements in WDS against EDS. Of course, the timing to get enough count is not the same by WDS compared to EDS. It's the EDS is very fast, and especially if you work at high beam current, like at 5 nanoamp with EDS, you can get very rapidly a spectrum. So it is not the problem here. The problem is that if you can't detect or measure one element by ADS, the solution is to go to WDS. Of course, if you can easily measure by ADS one element, if there are no overlap, if there are no problem to detect this element, use EDS. It's not a problem, but there are many problems, especially in the low range energy of the spectrum, where in fact, you cannot correctly measure, quantify, make any deconvolution, correct deconvolution, and so you have many problems like that. And so this is a reason why, in that case, you need to use WDS. So in that case, you spend some time on 1, 2, or 3 elements. And of course, the objective here is not to use a WDS as you are using EDS. You need both. It is why it is a complement to EDS.
Thank you, Eric. Thanks a lot, Eric and Michel, for your presentation. We have run out of time, so we conclude our Q&A. Remaining questions will be answered by email, and so please ask more questions if needed. So as a reminder, today's event was recorded and will be available very soon to get